This is part 1 of the 2.2 notes on chemical bonds and compounds. If you remember from yesterday, we talked about the elements, which are the substances that cannot be broken down any further into any simpler substance. And the smallest unit of the element is the atom. We represent atoms on the periodic table of elements. So here we have a chart that shows us all the different substances in their purest form. Now, the periodic table is arranged in a very particular way, and we talked about this yesterday. We have horizontal rows called periods, and we have vertical columns called groups. The scientists that developed this periodic table drew it in a very particular way to help us understand how atoms interact when they come in contact with other atoms. So, when we look at the periodic table, the horizontal rows, the periods, show us the configuration of the electrons, the orbitals. So each period represents a different orbital being occupied. So each orbital can only hold so many electrons. The vertical columns show us how many electrons are in each orbital. So for example, in group 1, which is highlighted here in red, each atom has only one electron in its outermost orbital. In group 2, we have 2 electrons in its outermost orbital. Group 3 has 3, group 4 has 4 electrons, and so on. The elements that are in white here, these are what are called the transition elements. These are a little bit more complicated, and luckily for us, we don't need to worry about these in biology. The electrons that are in the outermost orbital are referred to as the valence electrons. These are important because these are the electrons that are going to be interacting with other atoms. So we have a diagram that we can use to represent the electrons in the valence shell, and this is called the Lewis dot structure. So when we're looking at the periodic table, we can actually use the periodic table to tell us which elements are going to have how many valence electrons and in which orbitals. So the way that you write a Lewis dot structure is you start by writing the symbol of that chemical. So instead of drawing out like protons and neutrons, you're simply just going to write the chemical symbol. So here we have the example of carbon. Carbon has 4 valence electrons, and it is in the 4th column, so the 4th group. So the way that we're going to draw a Lewis dot structure is we're just going to use dots to represent the valence electrons in the outermost orbital. So you're going to start on one side, and then you're going to draw dots going around the symbol. This is representing the electrons in the valence orbital. So let's look at an example and kind of break down how to draw the Lewis dot structure and why we draw it the way that we do. So here we have the example of sodium. Sodium is number 11 on the periodic table. So what that tells us is that it has 11 protons, because if you remember, the atomic number is the number of protons in the nucleus. So sodium typically has, along with its 11 protons, has 11 neutrons as well. Remember, because of the positive charge of the protons, it's going to draw in negative charges in the electrons, because remember, opposites attract. So when we have a sodium atom, it's typically going to have 11 electrons as well. So remember, the orbitals get filled in a very particular way. So the first orbital is going to contain 2 electrons, okay, because that's the number that can fit in that smallest orbital. And then since sodium needs more than just 2 electrons, it's going to have another orbital, the second orbital, where we can fill a maximum of 8 electrons. And so if you add that up, 2 plus 8 gives us 10, but sodium can draw in 11 electrons, so we're going to have to put 1 electron in its outermost orbital. So sodium has 1 valence electron. And if you look at the periodic table, indeed, sodium is in group 1. So the way that we would write the Lewis dot structure for sodium is we're going to put the symbol for sodium, which is Na. Remember, sodium is one of those weird elements that its symbol is different than the English word that we use to describe it. So sodium is Na, and it has 1 valence electron, so we're simply going to put 1 dot by that symbol. So this is the Lewis dot structure for sodium. So let's look at another one. So let's look at chlorine. Chlorine is Number 17 on the periodic table because it has 17 protons. Again, chlorine typically has 17 protons and 17 neutrons. And because of the 17 positive charges that it has, it's going to draw in 17 negative electrons. Again, 2 in the first orbital, then 8 in the second orbital, and then the third orbital is going to have the 7 remaining electrons. So 2 plus 8 plus 7 gives us 17 electrons total. So how would you draw the Lewis dot structure for chlorine? Looking at these valence electrons only. You don't need to worry about all the other electrons. And the reason for that is it's the valence electrons that are going to interact with other atoms. And this makes sense because these are the electrons that are on the outside. So they are the ones that are likely to come in contact with other things. So looking at those 7 valence electrons, what you're going to do is you're going to start by putting 1 electron on one side of the chlorine. Now, typically, you either start at the top or you start on the right-hand side. It doesn't really matter which side you start on as long as you follow the same pattern. So you're going to put 1, and then you're going to add another, but you're not going to put it right next to the first electron. Because electrons, remember, are negatively charged, and like charges repel each other. So these electrons are going to try to space themselves out as far as they can go and still be attached to the same nucleus. So we have 2 electrons, and then we have 3 and 4. Once we've gone once around that elemental symbol, now we're going to have to start doubling up. So to put the 5th electron, we have to double up at the top, and then 6, and then 7. So this is the Lewis dot structure for chlorine. Now the Lewis dot structure is going to become useful because as we look at elements and how they interact with other elements, the Lewis dot structure is going to tell us a lot about what's going to happen next. So when we look at the periodic table of elements, there are 118 known elements. And of those 118, 92 of them occur in nature. That means if you just go digging around in the earth in the right places, you're going to dig up 92 different types of elements. The other 26 elements left are artificially made. So what this means is that they only occur when humans start tinkering around with their research. Now, if you look at something like, say, your own body, okay, you're made of more than just 118 different substances. There's literally thousands and thousands of substances that make up the human body. So where do all these substances come from? Well, they come from the combination of many elements into one bigger substance. And these are what we call compounds. Compounds are 2 or more atoms combined together to make a new substance. Elements that make the compound have their own unique chemical composition, but once you combine them together, they make something completely different than the elements that build them. So for example, water, familiarly, is H2O. The H is for hydrogen and the O is for oxygen. Both of these in their natural state are gases. Hydrogen is highly flammable. But when you add an oxygen to hydrogen, it's no longer flammable. It takes on different chemical properties. If you take sodium and chlorine and put them together, you get sodium chloride, which is table salt. Sodium by itself is a kind of a grayish, soft metal that is reactive in water. Chlorine on its own is a greenish gas that is toxic and is fatal if you inhale it. You put sodium and chlorine together, it forms a compound that becomes something totally different than the 2 substances that make it up. Not only is sodium and chlorine no longer reactive or deadly, it is now something that your body needs. You need a certain amount of salt in your diet to stay healthy. There are some elements that don't likely react, and those are the elements in the final column of the periodic table. That's column number 8. They have full electron orbitals in their valence orbital. So they have just the right number of electrons, and as a result, they don't really want to react with other elements. So when 2 elements come together, it's their valence electrons that are going to be doing the interacting. And what they're going to do is those elements are going to come together and they're going to form a compound. This is what we call a chemical reaction. A chemical reaction is where the valence electrons of those atoms are interacting. And what they're trying to do is they're trying to find a stable composition. So atoms, they like being neutral. They like having equal numbers of protons and electrons that balances them out. However, what they like even more than being neutral is to have a full valence orbital. So they want as many electrons in that final orbital as possible. And if all possible, they want it to be full, meaning not too many or not too few. So the way that atoms achieve this full valence orbital is by moving around their electrons. And this is what forms the bonds that hold chemical compounds together. And there are two main kinds of bonds that can form: ionic bonds and covalent bonds. Ionic bonds are where you're going to transfer electrons from one atom to the next. So that orbital, that valence orbital, that is missing electrons. So it either has a few too many or a few too few electrons. So an atom has to figure out how to solve this problem. I want a full orbital, so I can either fill up the orbital that I have, or I can empty that orbital out. So I can either gain electrons or I can lose electrons. And by doing so, it creates an atom that is charged. It's going to have an imbalance of protons versus electrons. So a charged atom is what we call an ion. The other kind of bond we'll talk about in more detail tomorrow is what is called a covalent bond. And covalent bonds are where atoms will share electrons. Rather than transferring electrons from one point to another, they're actually going to share those electrons together. And when you form covalent bonds, the compounds that result are called molecules. The term molecule specifically refers to compounds that have covalent bonds. Compounds that have ionic bonds are called ionic compounds. Now, a lot of people will make the mistake of saying any kind of compound is a molecule. I'm not a chemist, so I make that mistake all the time. I will sometimes say the word molecule when I really should be saying compound. A chemist would yell at me for this, but I can be forgiven in that in biology, most of the compounds that we have to deal with are actually covalently bonded, so they are technically molecules. So I'm not incorrect in that. So when we look at ionic bonds, let's take, for example, that sodium and chlorine that we saw earlier. So what you'll notice is that sodium has one extra electron in its outermost shell, that's valence electron, whereas chlorine has 7 electrons in its valence shell. Sodium would love to get rid of one of its electrons to empty out that shell, and chlorine would love to gain an electron to fill its shell. What would happen if a sodium atom comes close to a chlorine atom? Well, the outermost electron is going to be transferred. So what this does is sodium now loses an electron, and it becomes a positively charged ion. Now that sodium atom has 11 protons to 10 electrons. And if you do the math, 11 pluses and 10 minuses give us a net total of 1 extra positive charge. So that sodium ion is now a positively charged ion. Chlorine, on the other hand, it becomes a negative ion, because chlorine has 17 protons, and now that it's gained an electron, it now has 18 electrons. So if you have 17 pluses and 18 minuses, that gives you a net total of 1 extra minus charge. So chlorine becomes a negative ion. Positively charged ions are given the name cation, and negatively charged ions are given the name anions. The easiest way to remember that is think of a cation. The T looks kind of like a plus, so think of the plus as in positive. So what will happen is if you have this negative ion and you have this positive ion, remember we said opposites attract. Positively charged particles are attracted to negatively charged particles. And this goes for ions as well as protons and electrons. So that positively charged sodium is going to be drawn to that negatively charged chlorine. So we can represent this using the Lewis dot structure. So if we draw the Lewis dot structures again, sodium has 1 valence electron and chlorine has 7 valence electrons. So the Lewis dot structure makes it pretty obvious what's going to happen next. Sodium is going to transfer its one lonely electron to chlorine to kind of fill that extra spot. So now sodium has an empty orbital, which is fine. Sodium would rather have an empty orbital than have just one extra electron just kind of zooming around. And chlorine now has a full orbital. It has 8 electrons in that third orbital, which is a nice stable electron configuration. So both sodium and chlorine are now happier having lost an electron and gained electron than they would have had being neutral. But now these are ions, so we have to represent those ions. So what we do is we draw the symbol and we add the number of charges. So sodium has a +1 charge, so we write Na +1, and chlorine has a negative charge, so we write Cl -1. This is how ionic compounds are formed. The attraction between the sodium and the chlorine hold these two ions together. So if we look at another one, lithium, which is in the first column, so lithium has 1 extra electron, and then oxygen is in column number 6, so it has 6 valence electrons. So when we look at oxygen, oxygen is actually looking for 2 extra electrons to fill that outer orbital, and it's quite happy to take 1 electron each from a lithium atom. So what this does is lithium becomes a +1 because it's losing an electron, and then oxygen becomes a -2 because it's picking up 2 extra electrons. So it now has 8 protons, as all oxygen atoms do, and now it has 10 electrons. Those 10 electrons give it a negative charge. Something to think about when we look at the periodic table, the final column, these are the atoms that naturally have a balanced full electron orbital in its outermost orbital. These are what we call the noble gases. These are elements that naturally have a balance, so they don't really want to react. And another way to think about the reason that atoms react with other atoms is that they're trying to get an electron configuration to be more like those noble gases. So the way I like to think about it is that the noble gases are the cool kids and everybody wants to be like them. So sodium wants to be like all the other noble gases, so instead of hanging on to that 1 extra electron, it's going to get rid of it. So it's going to be more like neon on the other side of the periodic table, which has 10 electrons. If you look at chlorine, chlorine has 7 valence electrons, and it just desperately wants to gain 1 more electron, so it can have 18 electrons just like the cool argon atoms do. So all these atoms are trying to either fill or empty their outermost valence orbitals because that's what makes them stable and happy.